Now let's move on to another parameter in axial turbines. That parameter is known as the stator and rotor losses. But before we move further to discuss these two losses, we need to look to another type of efficiency. We previously know the total to total isentropic efficiencies. To be able for us to be able to discuss these losses, we need to look at this parameter that known as the total to static efficiencies. So this is actually the ratio between the living kinetic energy that is wasted and not contributing to the work output. And it is a functions between, or a ratio between, the enthalpy at the inlet of the stator minus to the enthalpy leaving the rotor divided by H00, or enthalpy at the inlet of stator minus to the H2SS, or the enthalpy leaving the rotor. On the other hand, as we previously look at the equations for the total to total isentropic efficiencies, or we can define them as the amount of kinetic energy at the outlet of the stage that being utilized to produce work. And it is a function of the enthalpy difference between inlet of the stator to the outlet of the rotor divided by the enthalpy at the inlet of the stator minus to the HO2SS, or it can be also seen from the total enthalpy point of view. And now let's look at the conditions of a normal stage where the absolute velocity is identical between the inlet of the stator to the outlet of the rotor, and the absolute flow angle is also the same. Therefore, we can rearrange the equation for the total to total efficiencies as a function of combining in this and this. We will have these equations, or in a simple term, we can write them down as functions between the enthalpy difference between the 0.2s and 0.2ss as a functions of temperature ratio and total enthalpy difference. And from these efficiencies equations, we can move on to the losses at the nozzle and the rotor. These equations, we know them as the dimensionless loss coefficients. That is a percentage drop of energy due to frictions in the blades, and this will result in total pressure and static enthalpy drop across the blades. And for the conditions at the nozzle, we calculate them as a functions of total enthalpy at the inlet of the rotor to the H1S and divide it by 0.5, multiply with the absolute velocity at the inlet of the rotor to the power of 2, or we can look them or calculate them as a functions of pressure ratio. And for the conditions at the rotor, we can get them by using the functions of the total enthalpy leaving the rotor to the H2S divided by 0.5, multiply with W2, or the relative velocity at the outlet of the rotor to the power of 2, or in the same manner to the nozzle conditions or the stator conditions, and we can look them or get them from the functions of pressure. To further analyze the stator and rotor losses, we can combine the blade loss coefficients to the total to total efficiencies and to the total to static efficiencies, and we will get this new equation for the total to total efficiencies as a functions of the rotor blade loss coefficients and the stator or nozzle loss coefficients. And the same is also applied to the total to static efficiencies, which we can also get the value according to the rotor and stator loss coefficients. And to begin our estimations with the blade loss coefficients, we can use these empirical equations. When the Reynolds number is around 10 to the power of 5, we can estimate the blade loss coefficients as a function of 0.04 plus 0.06 multiplied with epsilon divided by 100 to the power of 2, where epsilon is another terms that we can use as deflection angle, and it is equal, epsilon is equal to alpha 0 plus alpha 1 for the conditions at the stator, and epsilon will be equal to the relative flow angle beta 1 and beta 2 for the conditions at the rotor. The stator and rotor losses will also lead us into another parameter that known as the characteristic hydraulic diameter, or DH. That is the functions of 4 multiplied with S and L. S is the distance between the blades and L is the length of the blade itself, multiplied with the cos of alpha 1 divided by 2 multiplied with distance between the blade, cos alpha 1 plus 1, or we can simplify them as 2 times as S and L multiplied with cos alpha 1 and divided by S multiplied with cos alpha 1 plus 1. Geometrically, the S cos alpha 1 represent the distance between this plate here. The next parameter that also relates to the work of an axial turbine is what we call as the blade loading coefficients, or in some book they call them as the stage loading coefficients. This parameter represents the amount of work capacity of the stage in terms of temperature drop coefficients, and we can get these blade loading coefficients as a functions between work divided by the mass flow rate multiplied with blade velocity to the power of 2, or we can also calculate them from the heat capacity multiplied with the temperature difference between the inlet and outlet of the rotor divided by U to the power of 2. We can also get the blade loading coefficients as a functions between Cx2 minus Cx1 divided by U. Or we can also calculate the blade loading coefficients as a functions of the relative flow angle multiply with Ca divided by U, or we know that Ca per U is flow coefficients, and we can also write them as these functions. To show the value of the blade loading coefficients, we normally use this graph that represents the blade loading coefficients as a functions of flow coefficients, and each line or each curve here represents a difference total to total isentropic efficiencies. Another thing to keep in mind that a low value of blade loading coefficients means that a small amount of work done per stage. So a low value of blade loading coefficients will represent a small amount of work being done for each stage. As the value of the blade loading coefficient is small, and it is necessary to have more or increase the number of stage in an axial turbines to increase the power output. The conditions of low blade loading coefficients, for example, in these regions is favorable for power plants applications. On the other hand, for a higher blade loading coefficients is more favorable for aircraft or propulsion applications.